This is MA303's Quiz 2 from the summer of 2019. And yeah, this is just over more complicated solutions to linear systems and a little bit of classifying critical points. So question 1, we're finding the general solution to this system here. X prime equals AX. So what we need first off is to find our eigenvalues. We can get those with the determinant of a minus lambda I, set that equal to 0 and solve for lambda. So this is the determinant of 3 minus lambda, negative 1, 1, negative 5 minus lambda. This gives us a characteristic equation of 3 minus lambda minus 5 minus lambda plus 1 is equal to 0. Or lambda squared plus 2 lambda minus 15, minus 15 plus 1, so minus 14 is equal to 0. Now this doesn't factor nicely, so we're going to use the quadratic formula on it. So negative b over 2 will give us negative 1, plus or minus the square root of b squared minus 4 ac. That's just 4 times negative 14. Let's factor out a 4 just to make our lives a little easier. We'll get a 2 out here. We're dividing by 2, so both of these will cancel. These are our lambdas, and what will this be? Well, this is looking like the square root of 15 in here. 1 plus or minus the square root of 15. So in order to find our eigenvectors associated with these eigenvalues, let's just take one of our eigenvalues to start off with. Lambda 1 is equal to negative 1 plus root 15, and plug that into a minus lambda I. So 3 minus negative 1 plus root 15 will be 4 minus root 15. And then we still have our negative 1, our 1, and then minus 4 minus root 15, like so. So now that we have a minus lambda I, we can find our first eigenvector using row 1. That's just going to give us 1, 4 minus root 15, like so. We'll say that's v1. And then if we want our second a minus lambda I using our other eigenvalue, lambda 2 is equal to negative 1 minus root 15. Well, the only thing that's changing here is the sign on this root 15. So a minus lambda I is pretty easy. It's just 4 plus root 15 minus 1, 1 minus 4 plus root 15. And all that will do is change the sign on root 15 in our eigenvector. So 4 plus root 15 is equal to v2. Now we know that our solution will have the form x of t is equal to c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. So we can say that x of t, that's not a t, x of t is equal to c1 1 4 minus root 15 e to the lambda 1t plus c2 v2 e to the lambda 2t. And we are done. Let's go grab the second question and bring it down here a little bit so we can see it without scrolling up every time. Okay, question 2, solve the linear system and determine the type of critical point at 0, 0. And figure out whether it's stable, asymptotically stable, or unstable. So the first skill that they're kind of testing here is your ability to take a system of differential equations and put it into matrix form. So let's rewrite this a little bit. We'll say that x prime is equal to 0x plus y, and y prime is equal to minus 5x minus 4y. Now, you don't even have to do any more thinking. If you put it like this, you can already kind of see the matrix form. We can just say that x prime is equal to 0, 1, minus 5, minus 4 times x. And if x is a vector, it's weird calling it x, but I think you know what I mean. If x is a vector formed from x and y, if you do the matrix multiplication here, you will get exactly this back out. So let's find our eigenvalues. Again, that's the determinant of a minus lambda I equals 0. So we're really solving 0 minus lambda times negative 4 minus lambda plus 5 is equal to 0. Or lambda squared plus 4 lambda plus 5 is equal to 0. And will this factor? I don't think so. So let's do our quadratic formula again. We'll get negative 2 plus or minus the square root of 16 minus 4 times 5 over 2. This gives us negative 4 in here, which becomes 2i. Dividing by 2, we get our eigenvalues, which are negative 2 plus or minus I. So when we're solving things with complex eigenvalues, all we need is one eigenvalue and one eigenvector. So let's just use lambda 1 is equal to negative 2 plus I. Now, a minus lambda I, that will give us 2 minus I, 1, negative 5, negative 2 minus I. And we can use either one of these rows to find our eigenvector, and we'll get a different looking solution that will actually be identical. And using row 1, because the numbers are a little smaller, is what I'm going to go with. So this will give us an eigenvector of negative 1, 2 minus I. So now we're pretty close to having our solution, actually. Let's just set up v1 times e to the lambda 1t. So that's negative 1, 2 minus I, e to the negative 2 plus I t. I'm going to rewrite this a little bit as negative 2t plus it, and then split this off as multiplying by e to the it. And since e to the it is equal to cosine of t plus I sine of t, that's Euler's identity or formula, I can't remember which, we can replace that here with cosine of t plus I sine of t. Now all we need to do to get our full general solution is to split this thing up by expanding and distributing these cosines and sines into our vector. Split it up. Oh, this shouldn't be an I. This should be a t here, negative 2t. There we go. Split it up based on its real and imaginary parts. So what I mean by that is we can say that x of t is equal to c1 times all of the real bits of this thing right here. We'll get real things when we multiply cosine on top to that negative 1, cosine to that 2, and I sine to that negative I. So that will give us negative cosine of t, and then on the bottom, 2 cosine of t plus sine of t, because that negative I squared sine t will give us positive sine t. And then we can't forget that we've got an e to the negative 2t on the end of there. And then we have our imaginary portion. We get imaginary things when we multiply sine on top. So we'll put negative sine t. Remember, you don't want to keep that I around for your final answer. And then we'll also get imaginary things when sine gets multiplied to that 2 and cosine gets multiplied to that negative I. So we get 2 sine t minus cosine t e to the negative 2t. And what is the behavior of this system? Well, just looking at our eigenvalues here, we have complex conjugate eigenvalues with a negative real part. That means that whatever critical point we're dealing with, in our case, it's easy, it's just the origin, is going to be a spiral sink. And you can kind of see this in the form of our, sorry, there's a car alarm going off. You can see that in the form of our general solution down here. The spiral behavior of the spiral sink is coming from these cosines and sines here, and the sink portion of the spiral sink is coming from the e to the negative 2t's, because as that t increases, e to the negative 2t will approach 0. So it doesn't matter what constants we have outside here, we're always going to be spiraling in to the origin as time goes on. And let's go check that this is the correct solution, or a correct solution, because remember, if we used our other, the other, like the eigenvector that would have been formed from this row, we would have something that looks different but would actually act exactly in the same way. Yep, so this is correct according to the answer key, and our final answer for its stability would be asymptotically stable, because we're dealing with a spiral saying things will approach that as time approaches infinity. Yeah, okay, so that's quiz 2 for you, and I'm actually publishing this after quiz 2, so I'm not sure how useful this will be.